Morning girls. Recurrence relations. Simply recurrence relation is nothing but it's a recursively defined sequences are called recurrence relation. That means one term of a sequence is expressed as one or more terms of the remaining terms of the sequence. That means suppose for example if nth term of a sequence is expressed as the sum of its preceding terms, that means a n minus 1 plus a n minus 2, that means nth term is the sum of its preceding first two preceding terms. Or other examples, here nth term of a sequence is equal to 3 times of a n minus 1 minus 2 times of a n minus 2. That means nth term is expressed as the difference of n minus 1th term and also at n minus 2th term. That means 3 times of n minus 1th term and 2 times of n minus 2th term, right? That means the term of a sequence is expressed as one or more terms of the sequence. This is called a recurrence relation. Now, what is the definition? A recurrence relation is a formula that relates for any integer n greater than or equal to 1, the nth term of a sequence to one or more terms of the sequence. That is a0, a1, a2 and so on, an minus 1. Right? Now, to its preceding terms only. Here second example is an is equal to a0 an minus 1 plus a1 an minus 2 plus so on an minus 1 into a0. This is an example only. Now next, an square is equal plus an minus 1 whole square is equal to minus 1. This is a relation between nth term of a sequence to its preceding terms only. Right? Now the next example, an is equal to n minus 1 into an minus 1 plus n minus 1 into an minus 2. That is, the nth term of a sequence is expressed as something into n minus 1th term plus some constant into n minus 2th term, right? Now that is an is expressed as sum of its preceding terms, that is n minus 1th term and also n minus 2th term. Now here an is equal to 3 times of its preceding term an minus 1, where n greater than or equal to greater than 0. That is, the nth term of a sequence is equal to 3 times of its preceding term. Preceding term is an minus 1. Next example is an plus 1 is equal to 3 into an. Right? Now n plus 1th term of a sequence is equal to 3 times of its preceding sequence. Right? Here we are expressing this one nth term here n plus 1th term of a sequence. The nth term of n plus 1th term of a sequence is equal to 3 times of its preceding sequence. Now some definitions are there. A recurrence relation is of the form c naught n a1 an plus c1 of n an minus 1 plus ck of n an minus k is equal to f of n for n greater than k. This is n greater than or equal to k, where n and k belongs to w. Here w stands for whole numbers, or you can write n comma k are non-negative integers, where c naught of n, c1 of n, ck of n and f of n are the functions of n. It is said to be a linear recurrence relation. A recurrence relation is of this form is called a linear recurrence relation. Right? Now see, if c naught of n and ck of n are not identically 0, then it is said to be a linear recurrence relation of degree k. that means the kth term coefficient is not equal to 0 and the initial term is not equal to 0, then the linear recurrence relation is said to be of degree k. That means this coefficient here, the n minus a coefficient is not equal to 0 and also this one not equal to 0, then that is said to be a recurrence relation, a linear recurrence relation of degree k, right? Next, if c naught of n comma c1 of n so on ck of n are constants, then the recurrence relation is known as linear recurrence relation with constant coefficients. That means in this standard form, if these are constants, that means some 2 into an plus 3 into an minus 1 plus so on 4 into an minus k. That means the coefficient of an minus k, the coefficient of an minus 1, the coefficient of an are constants, then that is said to be a linear recurrence relation with constant coefficients. For example, see this one. Here, this is a linear recurrence relation with constant coefficients because its coefficient is a constant, its coefficient is also a constant. Here an coefficient is 1 here, therefore this is called a linear recurrence relation with constant coefficients. Here also, here coefficient of an is 1, here the coefficient of an minus 1 is 3, therefore this is called a linear recurrence relation with constant coefficients, and this one also a linear recurrence relation with constant coefficients. Now, if f of n is identical equal to 0, that means f of n value is equal to 0, then the recurrence relation is said to be a homogeneous recurrence relation, otherwise it is non-homogeneous. See, in a recurrence relation, if the last is equal to value is equal to 0, then that relation is said to be a homogeneous recurrence relation. See here, if an is equal to 3an minus 1, that means there is no constant here, that means plus 10 plus 5 is not there, therefore this is a homogeneous recurrence relation. This one also a homogeneous recurrence relation, right? This one is also a homogeneous recurrence relation, whereas this one is not a homogeneous recurrence relation because constant is there, no, right? This one is a homogeneous recurrence relation because there is no constant or there is no separate function of n terms. Now, next one, first order linear recurrence relation. In a recurrence relation, the n plus 1th term or the nth term depends on only on its immediate predecessor. That means that before term, then that relation is called a first order linear recurrence relation. Once again, in a recurrence relation, if the nth or n plus 1th term depends only on its immediate predecessor, then the relation is said to be, or the recurrence relation is said to be, the first order linear recurrence relation. Example, an plus 1 is equal to 3 times of an. N plus 1th term is dependent on its predecessor only, right? An plus 1th is equal to an minus 2, right? Now, there n plus 1th term is depends on its predecessor, that is an. Now, the general form of first order linear homogeneous recurrence relation. See, homogeneous recurrence relation means there is no constant. With constant coefficients is an plus 1 is equal to d into an, where n greater than or equal to 0. Here d is a constant, this d is a constant. That means here, see once again, the general form of first order linear homogeneous. Homogeneous means is equal to 0, f of n is equal to 0. Recurrence relation with constant coefficient means the coefficients of an minus 1 all must be constants. Here d is a constant. The n plus 1th term of the sequence depends on its predecessor only. Therefore, it is a first order linear differential equation and there is no constant term, therefore it is homogeneous. The coefficient of an is also a constant, therefore this is called a linear homogeneous recurrence relation with constant coefficients. Now, in a recurrence relation, the values of a naught, a1 given at an initial stage in addition to the recurrence relation is called boundary conditions, or you can say initial condition. Suppose one problem is given to you like this: an plus 1 is equal to 3an where n greater than or equal to 0. Of course, this is a linear recurrence relation of first order with constant coefficient and also it is homogeneous. Suppose at the initial stage only some extra condition is given to you like this, and a naught is equal to 5. One initial condition is given at the initial stage, therefore these are called boundary conditions, or you can say initial conditions. What are boundary conditions? The values a naught value or a1 value is given at the initial stage. Initial stage means in addition to the recurrence relation తో పాటుగా ఇస్తే then those values are called boundary conditions, or you can say initial conditions. Next one, the unique solution of the recurrence relation an plus 1 is equal to d into an where n greater than or equal to 0. D is a constant and a naught is equal to a, capital A. This is the initial condition, no? Right. This is the initial condition, or you can say boundary condition of the given recurrence relation. Is the solution is an is equal to capital A into d power n. What is capital A? Capital A is nothing but a naught value. And d power n, what is d? D is a constant, it is the coefficient of a power n of the given recurrence relation where n greater than or equal to 0. This is the standard form, right? If the given recurrence relation is in standard form, then its solution is nothing but an is equal to capital A into d power n. Solve the recurrence relation. an is equal to 7 into an minus 1 where n greater than or equal to 1 and a2 is equal to 98. Now we have to find the solution of this recurrence relation. Of course, this is a linear first order homogeneous recurrence relation with constant coefficients. Now we are writing the given data. Given that an is equal to 7 into an minus 1, n greater than or equal to 0, a2 is equal to 98. Now we are converting this one to standard form. What is the standard form? an plus 1 is equal to d into an where n greater than or equal to 0. See, now here n is replaced by n plus 1. What will get? That means n is in the given recurrence relation, n I am replacing by an plus 1. n is replaced by n plus 1. an plus 1 is equal to 7 into, in the place of n I have to write n plus 1, no? n plus 1 minus 1. 1 gets cancelled, I will get n only. Similarly, here n greater than or equal to 1 is given. In the rough work, n greater than or equal to 1, no? n is replaced by n plus 1, no? That means n plus 1 is greater than or equal to 1. Transpose this one to right side. n greater than or equal to 1 minus 1. n greater than or equal to 0. Alright, now an plus 1 is equal to 7 into an, n greater than or equal to 0. Now this is in standard form, right? Now compare this one. D value is equal to a7 and the solution of this equation is always given by an is equal to capital A into d power n, right? The solution is an is equal to a into d power n, where a is equal to a naught and d is equal to the coefficient of a power n, which is in standard form, right? Now here a value is 7, d value is 7. Now I have to find a naught. Now see, an is equal to a naught into a, capital A value is a naught into 7 power n. Given that a2 is equal to 98, that is initial condition is given at the initial stage only. Put n is equal to 2 here. What I'll get? a2, that is 98 is equal to a naught 7 power 2. 7 square means 49. That implies a naught is equal to 98 by 49, that is equal to 2. Therefore, the solution is an is equal to a naught value is 2, 7 power n, where n greater than or equal to 0. This is the unique solution of the given recurrence relation. Next one, find the unique solution of the recurrence relation 6an minus 7an minus 1 is equal to 0, n greater than or equal to 1, a3 is equal to 343. Here once again we have to find the unique solution of the given recurrence relation. Now given that 6an minus 7an minus 1 is equal to 0, n greater than or equal to 1, and initial condition is given. This is called boundary condition. a3 is equal to 343. First of all, we are converting this given recurrence relation to standard form. What is our standard form? That is an plus 1 is equal to d into an is the standard form, where n greater than or equal to 0. For that, 6an is equal to 7an minus 1. an is equal to n by 6 into an minus 1, where n greater than or equal to 0. To get this one, to convert this one into standard form, n is replaced by n plus 1. an plus 1 is equal to 7 by 6 into n plus 1 minus 1. 1 gets cancelled, an you will get. Here similarly, n is greater than or equal to 0. n is replaced by n plus 1. n plus 1 is greater than or equal to 1. n greater than or equal to 0. Now this is in standard form, right? Standard form means n plus 1 is equal to d into an, n greater than or equal to 0. This is in standard form, right? Standard form. Now the solution of this equation is given by an is equal to capital A into d power n, where a naught is equal to capital A, d is equal to coefficient of an, that is 7 by 6. Therefore, solution is equal to an is equal to a naught into 7 by 6 whole power n. But a3 is equal to 343, no? Right. a3 is equal to, that is 343 is equal to a naught 7 by 6 whole power 3. 343 is equal to a naught into 7 cube means 7 into 7 into 7, that is 343. 6 into 6 into 6 is 216. 343 gets cancelled. A naught is equal to 216. Substitute this value here, you will get the solution. Therefore, the unique solution is given by an is equal to a naught value is 216, 7 by 6 whole power n. Whole power n is the solution of the given recurrence relation.